We have driven rovers across Mars. We have dropped a probe through the crushing clouds of Saturn. We flew a spacecraft past Pluto, 3.5 billion miles away, and photographed its surface in stunning detail. We have touched nearly every corner of this solar system, and yet there is one direction no spacecraft has ever truly gone. Not to a distant planet, not to the edge of the galaxy, just up, straight up, directly above the sun, out of the flat disk where all the planets live, perpendicular to everything we have ever explored. The vertical exit from our solar system. It sounds like the easiest thing imaginable. Point a rocket upward and go. But physics has other ideas, and what physics does to anyone who tries to escape vertically is one of the strangest, most counterintuitive stories in all of space exploration. This is why going straight up is harder than reaching Pluto. This is what is waiting up there. And this is the bizarre maneuver scientists are now proposing. One where a spacecraft has to fall toward the sun before it can ever climb away from it. Act 1. The prison of orbital velocity. Here is something you never feel, but it is happening to you right now. The Earth is moving sideways around the sun at 30 kilometers per second. That is roughly 67,000 miles per h-hour every single second. The ground beneath your feet is hurtling 30 kilometers in a direction that has nothing to do with up or down. It is pure sideways momentum, locked into the planet by 4.6 billion years of orbital history. Every rocket we launch inherits that motion completely. The moment a spacecraft lifts off from Earth, it is already traveling 30 kilometers per second sideways, the same as the planet it just left. Engineers actually love this. When we want to reach Mars or Jupiter or Saturn, that existing motion does most of the heavy lifting. A few additional kilometers per second in the right direction, and the probe is on its way. The solar system is flat. The planets are all in roughly the same plane, and Earth's orbital speed is essentially a running head start. But try to go straight up, and everything changes. To climb directly out of the planetary plane, perpendicular to Earth's orbit toward the north or south pole of the sun, you first have to cancel the 30 kilometers per second you are already carrying. Every single bit of it. Then, once you have canceled it, you have to build new velocity to actually climb. The energy required does not merely double or triple. It becomes almost incomprehensible by the standards of rocket fuel. Mission designers measured this challenge in delta V, the change in velocity a spacecraft must generate on its own engines. Getting to Mars from Earth orbit requires roughly 4 kilometers per second of delta V. Escaping vertically straight up out of the ecliptic plane requires approximately 30 kilometers per second, nearly 10 times as much. Let that settle for a moment. Reaching Pluto, a world so distant that sunlight takes over 5 hours to get there, requires less energy than reaching a point just a few million miles directly above our own sun. The solar system is not a prison of walls or locks. It is a prison of momentum. And Earth's orbital speed, the very thing that makes every other mission possible, is the thing that makes vertical escape nearly impossible. Act 2. The mystery at the top of the sun. Because climbing out of the plane is so brutally expensive, almost no spacecraft has ever done it. Which means that the regions directly above and below our sun, the solar poles, remain even today one of the least explored frontiers in the entire solar system. Pause and think about what that means. We have high-resolution maps of Mars. We have photographed the geysers of Enceladus, the storms of Jupiter, the razor-sharp rings of Saturn. We have landed on an asteroid and returned its dust to Earth. We have imaged comets from close range. But the poles of our own sun, the nearest star, the one that makes all life on this planet possible, were essentially invisible to us until very recently. This is not a minor gap. The polar regions of the sun are where some of the most powerful and consequential solar activity originates. The fastest solar winds, streams of charged particles that blast outward through the solar system, pour out of the polar coronal holes at speeds between 700 and 800 kilometers per second. The Sun's magnetic field, which reverses its polarity every 11 years in an event that reshapes space weather across the entire solar system, is driven by processes that begin at the poles. The entire electromagnetic environment that Earth and every other planet lives inside is fundamentally shaped by what happens at the top and bottom of our star. And for most of human history, we have been watching it from the side, trying to understand the full behavior of a star by staring at its equator, the way you might try to understand a hurricane by only ever looking at its outermost edge. Only 2 missions have ever managed a real polar view. The first was Ulysses, a joint NASA and ESA spacecraft launched in 1990. To escape the ecliptic plane at all, Ulysses had to take a wildly indirect route, traveling all the way out to Jupiter first, then using the giant planet's gravity to slingshot itself nearly 80 degrees out of the planetary disk, before falling back inward toward the Sun on a dramatically tilted orbit. The mission worked. Ulysses gave us the first real measurements of the fast solar wind streaming from the polar regions, confirming that something genuinely different was happening there. But the spacecraft carried 1980s instruments with no cameras capable of actual imaging. We got data from the poles. We never saw them. The second mission is happening right now. Solar Orbiter, a European Space Agency probe launched in 2020, has been using repeated gravity assists from Venus to tilt its orbit higher and higher out of the ecliptic. In March 2025, it sent back the first direct images of the Sun's south pole ever captured in human history. The photographs show a region of chaotic, tangled magnetic complexity, nothing like the comparatively smooth solar surface visible from Earth's vantage point. Strange, knotted structures that had never been observed before, a face of our Sun that humans had simply never seen. Think about that honestly. The brightest object in our sky, the engine of every ecosystem on this planet, the center of our entire solar system. And until just last year, nobody, no human, no robot, no instrument of any kind, had ever looked directly down at its pole and taken a picture. That is how incomplete our picture of even the nearest star still is. Act 3. The shape of our home. There is a second reason the vertical view matters, one that goes even deeper. We do not actually know what our own solar system looks like from outside. The Sun does not just sit passively in space, it exhales constantly. A continuous stream of charged particles. The solar wind flows outward in all directions, pushing back against the interstellar medium, the thin gas and dust that fills the space between stars. The region where the Sun's wind dominates, where its influence holds back the galaxy, is called the heliosphere. It is an enormous magnetic bubble that contains every planet, every comet, every spacecraft humanity has ever launched. Everything we have ever touched is inside it. Beyond the heliosphere lies something genuinely alien, the interstellar environment, saturated with cosmic rays and high-energy particles that our bubble deflects. The heliosphere is, in a very real sense, the shield that makes the solar system livable. For decades, we assumed this bubble was shaped like a comet. A blunt, rounded leading edge pushing into the interstellar wind in the direction the solar system is moving through the galaxy, and a long sweeping tail stretching out behind it. It was a reasonable assumption. It appeared in textbooks. It appeared in spacecraft diagrams. It became the default image of our cosmic home. Then in 2020, a research team led by astrophysicist Merav Ofer at Boston University ran a new model using accumulated NASA data and arrived at a completely different answer. The heliosphere is probably not comet-shaped at all. Their model suggests it looks more like a deflated croissant, a curved central bulge with 2 short jets curling away from it, with no long trailing tail. The reason we cannot say definitively which picture is correct is straightforward and slightly humbling. We have never seen the heliosphere from outside. The Voyager probes which crossed the heliopause and entered interstellar space did so almost entirely within the plane of the planets. Their crossing points gave us 2 data samples, both near the equatorial belt, useful, but nowhere near enough to reconstruct the overall shape of the structure. To actually map the heliosphere, to understand the true form of the bubble we live inside, we would need a spacecraft high above the ecliptic plane, looking down at the whole structure from a useful angle, seeing it the way you would see a city from an airplane, rather than by walking through its streets. We live inside a structure whose real shape we have never confirmed. That is where we are. Act 4. To climb, you must first fall. So how do you actually solve this problem? Building a more powerful rocket does not work. The delta-V requirement, 30 kilometers per second, is beyond any realistic chemical propulsion system we have or are likely to build in the near future. You cannot simply brute force your way out of the plane. The numbers do not cooperate. The solution that serious mission designers are now actively exploring is something that sounds, at first, like it is going in the completely wrong direction. You fall toward the sun. Instead of pointing your spacecraft upward and trying to climb immediately, you do the opposite. You aim it inward. You let solar gravity pull the spacecraft into a steep dive, accelerating it relentlessly as it falls closer and closer to the sun. By the time the spacecraft reaches its closest approach point, called perihelion, it is moving at extraordinary speed, potentially over 100 kilometers per second, faster than any human-made object has ever traveled. And at precisely that moment, you fire the engines. This works because of a principle first described by German rocket pioneer Hermann Oberth in 1929. A rocket burn is dramatically more efficient when performed at high velocity inside a deep gravitational well. The same quantity of fuel that produces a modest velocity change in the emptiness of space produces a vastly larger increase in orbital energy when burned at perihelion. The gravitational depth amplifies the burn. The speed amplifies it further. The result is a burst of kinetic energy far beyond what the fuel alone could generate anywhere else in the solar system. The dive becomes the launch pad. After the burn, the spacecraft is moving so fast, in such a well-angled direction, that it can finally shed its sideways orbital momentum and climb, genuinely climb, out of the ecliptic plane, heading directly toward the solar poles, or straight out of the solar system entirely. Solar sails are also part of the emerging architecture. Proposed missions like the Solar Polar Imager and the high-inclination solar mission envision enormous reflective sheets, thousands of square meters of thin metallic film that use the pressure of sunlight itself to gradually tilt a spacecraft's orbit. No fuel. No engine. Just photons pressing against a surface, slowly but persistently bending the trajectory over months and years. Sails alone are patient. The Oberth maneuver alone is violent. But combine them, a spacecraft that rides a solar sail to spiral inward close to the sun, executes a precisely timed Oberth burn at perihelion to redirect itself vertically, then unfurls the sail again to ride the outward climb. And you have a mission architecture that astrodynamicists genuinely believe could work. The solution to escaping the solar system upward is to first plunge downward as deep as physics allows. Act 5. What waits above? If a spacecraft ever makes this climb, if the maneuver works and the probe rises cleanly above the ecliptic, what does it actually find up there? The first thing that changes is the environment itself. The planetary plane is cluttered. Every planet, including Earth, moves through a thin, persistent haze of dust. The accumulated debris of billions of years of comet passages, asteroid collisions, and the slow grinding erosion of small bodies. On an exceptionally dark night, you can actually see this dust with your naked eye. Just after sunset or before sunrise, a faint, pale pyramid of light rises from the horizon along the path of the ecliptic. This is the zodiacal light. sunlight scattering off the dust disk of our own solar system. You are looking at the inside of our neighborhood, glowing softly. A spacecraft climbing out of the ecliptic would leave this dust behind within months. The view above is radically cleaner, less scattered light, less background noise, less interference. From that altitude, a telescope designed to search for biosignatures around other stars would have a far clearer window than any instrument operating from inside the disk. The dust that fills our plane drowns out exactly the kinds of faint signals astronomers most want to detect. The solar environment changes too. In the equatorial region, the solar wind is slow, dense, and turbulent. A roiling stream of plasma moving at roughly 400 kilometers per second. Above the polar coronal holes, it transforms. The fast solar wind flows outward in a thinner, smoother, steadier current at 700 to 800 kilometers per second. A spacecraft riding through this stream would operate in a fundamentally different radiation environment, one that reshapes both what the instruments can detect and how long the spacecraft's electronics can survive. And then there is the view. From high above the ecliptic, the solar system would finally be visible as what it actually is. A disk, a flat ring of planets orbiting a single star, dust hugging the plane. The entire structure wrapped in the uncertain shape of the heliosphere. For the first time in history, a spacecraft could look down at the solar system the way we look down at Earth from orbit. We have photographs of galaxies billions of light years away. We have images of the cosmic web, the largest structures in the observable universe. We have looked back at the Big Bang itself through the cosmic microwave background. But a photograph looking straight down at our own solar system from outside its plane, our home, the place every human being has ever lived, does not exist. No camera has ever captured it. Not once. That image is still waiting to be taken, and the mission that takes it will first have to fall toward the sun before it can ever climb above it. If you were designing that mission, which approach would you trust? The slow, patient arc of a solar sail, or the violent, all-or-nothing plunge of the Oberth dive? And if you want to know what actually exists in those unexplored regions once you get there, the strange physics, the unknown structures, the science waiting above and below our solar disk, that is exactly what the next video covers. This one explained the journey. The next one shows you the destination.